Okay, so now we take in an example of a sublist, or my problem is that I need to find out whether a list L is a valid sublist of another list L. So let's write it down. Sub is L or is L1 a valid sublist of the list L? Of course, I will use a pen, so let's draw it up. So this is the large L list L, and L1 is some sublist over here. Of course, I like to use append and use lots of variable names, as many as possible. So let's say this is Lx, and Lx appended to L1 gives me Ly. So this is Ly, and Ly appended to take as many variables. Lz gives me L. If I can find such Lx, Ly, Lz, then it's okay. So L1 is a sublist of L if and only if I can append some Lx to L1, which gives me this bigger list Ly, and comma is and I can simultaneously append Ly to Lz to give me L. And let's remove singletons, variables which only have one occurrence. So Lx occurs only once, I'll remove that. L1 occurs here, Ly occurs here, Lz only occurs once. Maybe I could remove that and rest everything is okay. Let's quickly type that up. So I have a sublist L1L is, can I append some list to my list L1, the smaller sublist, to produce a list Ly. At the same time, the larger list that comes out Ly appended to Lz gives me some list, gives me the list L. It's a fact, so let's do it. Is 3, 4, 5 a sublist of 1, 2, 3, 4, 5, 6? Yes. So the answer is true. Let's try it the other way around. 9 and oops. So it appears that I did go into wrong stack limit exceeded. It went into an infinite loop. Now you'll have to be very careful that, of course, every time in data structures we would say make sure larger problem divided into smaller problem, and there's no way that you go upon from a smaller problem to a larger problem because it will never end. We weren't doing so far, so let's check out whatever we have done and to see if this thing was true. Append, I already explained that when I was talking about member. So my biggest list L is fixed. That's the biggest list. So whatever Prolog can do on the smaller list, they guaranteed have to be smaller. And there wasn't a recursion happening, so the chances of going wrong were small. And similarly here, now the problem that happens is, in order to prove this, I need to prove first this and then this. And as you can see, there's no limit on what Ly can be. So when it's false, which means it's exhaustively searched for everything, I'm not binding Ly. It could go arbitrarily large. Of course, later on it will turn out to be false when you look at the second component of the AND. So it's an AND or search. In backtracking, if you fail in the branch, then only you go to the other branch. But in case the first branch can go infinitely, your AND or graph will go infinite. And that's what's happening. Ly is going infinite in depth. So what do I do? Luckily here, the largest branch is fixed as given in the input. So they are limited ly. For 1, 2, 3, 4, 5, 6, ly could be 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 empty. So let's have the problem which is bounded first. Now what happens is ly is bounded. It's definitely less than L, so its size becomes bounded, and ly is your bounded bigger list. So when ly is bounded, these two can be much smaller. Let's run the same thing again. False. Did I affect the truthness of it? So of course I could have given you the answer straight away, but whenever you enter into an infinite loop, it's always good to find out why and make sure you have some corrections. Let's continue to take in some list examples. So we've already modeled the member thing. Let's redo it up, this time using recursion. So I do it because if something is a member of visited, then of course you don't need to insert it again, so it relies on member. So let's redefine member. So there's an x here, and if x lies over here, then of course it's true. So I divide the list into two parts. The first part, or the head, and the second part, or the tail. And this is my list L. Y1, it could be just H and L. So is X a member of L? So I solved the first part. Yes, it is a member if head is equal to X. Then it is a member. So the list was broken down into two parts. So L became HL. And if H is equal to X, then yes, the statement is true. Or, so all I do it by redefinition. If X is a member of L, tail. Oh God, what's happening? Head, tail, and head. Tail. Now I'll just ensure that the conventions are doing absolutely okay and there's no problem with the convention. So I've never written equality over here in Prolog. So h is equal to x. Let me just embed that over here. So h is equal to x. Let me just embed that over here as I do it. And that's your other member definition. So this one doesn't hold good. Let's delete it. And I say member X is. So this one is simple to read. So if the head of a list is X, then of course X is a member of it. On the other hand, member X comma a list which has some head followed by some tail. This is true if X is a member of the tail. So X should actually be a member of the head or the tail. Those are the two conditions. Both of them are facts. Let's very quickly, is one a member of 1, 2, 3, 4, 5? Or just 1, 2, 3, 4? The answer is true, of course. Is 5 a member of this? So let's find out. False. 5 is not a member of it. Find out all x such that x is a member of this. So x is 1, 2, 3, 4 are all members of this. And if you want to do find out all L such that 5 is a member of it, believe me, it's a very bad idea because again you'll have the anonymous variable names that will come up. So this says some variable doesn't matter followed by a variable 5 followed by as a tail any variable that doesn't matter, and this will go on and on. So that is what is my member. We've done add is easy. So if you want to add 5 to a list, so it just becomes 5 followed by the list. We've already done that. So there's absolutely no point in telling you what is add. Delete is more interesting. So I need to delete X from the list L. I need to define this one. So of course I will take in an actual list L. We will do it as, of course, recursively. So let's define it in terms of a head and a tail. And how do I carry on delete is obviously the simple fact. You first try to delete it from the head. If you can, done. And if you cannot, then you try the tail. So you only have to look at it. So I first try to delete it from the head. So let's write it down in the full formal way, and then I will write it down in the other way possible. So this is writing it down in the actual formal way, head, tail. So if X is equal to head, wonderful, then I just need to return my tail. And if I need to return my tail, now remember I need to give an answer. So the answer will be the new argument. So let's say A is what is my answer. After deleting, A has to be the answer. So in this case, either you write down answer is equal to tail. So if H was head, H is deleted, and if H is deleted, what is left? Absolutely just nothing but the tail. And otherwise, if you cannot delete it from the head, then try to delete it from the tail. So what do I do is I simply delete it from the tail, and whatever answer comes out from the tail is what is my actual answer. So let's break down the answer also into the same fact. So this is my answer variable. My answer variable also has a head answer and a tail answer. So we're considering the case where it did not occur in the head, or for some reason you did not want to delete it from the head. So H will become is equal to HA, and okay, now let's compress this thing up. X is equal to H, X is equal to H, and A is equal to T. So A is equal to T, and of course it implies true, so it's dot. So this thing should be read as from the list with head X and tail T, if I delete X, which is practically there at the head, the answer is just the tail. From the list, which is with the head X and the tail T, if I delete X, the answer is the tail T. This is how it should be read. Now coming up on how this one should be read as. So again, let me do it. H is equal to HA. So this becomes nothing but H is equal to HA, and TA still has the answer. So now let's try to read it down as a rule. Once I write down the answer, it becomes absolutely too simple. So let's try to read this as a rule as well. From the list, which has a head H and a tail T, if I delete X from it, I get the result as the same head followed by, so I mean there is a X and I deleted it up, so I get the same head followed by a new tail TA, where tail TA is what I get from this tail T after I delete X from it. So from this tail T, I delete X, I get TA. From this list T, I delete X, I get TA. So in short, recursion, you apply it on the tail, and the head you did not delete it up. So you apply it on the tail, get the deleted list as the output, and just join the head. Apply it on the tail, get the deleted list as the output, which is TA over here, and then just add head to TA. And this is your description. So let's quickly write that down. Delete X with X and T. So from the list with head X and tail T, if I delete X, I get the answer as T itself. However, if I delete X from a list which has head H and tail T, I get in the answer as a new list which has the same head H, and tail gets a new TA, where TA is, now let me recursively compute for TA. From T, if I delete X, I get TA. So let's quickly get it. So delete 3 from 1, 2, 3, 4, 5, 6. What do I get? Last one is, what is the answer? That is a false. Delete X, XG, that shouldn't happen. Oops, what did I do? Okay, so yes, that's absolutely true, and there's one just answer only. So 3 deleted from 1, 2, 3, 4, 5, 6 gives me this. What if I delete 8? So 8 deleted from this, 8 is not there, so you of course get a false. Let's do it the other way around. So what deleted from 1, 2, 3, 8, 4, 5, 6 will give me 1, 2, 3, 4, 5, 6. X is equal to 8. That is absolutely correct. Is there any other answer? That's absolutely no. Let's do it still the other way around. So let's say 2 deleted from gives me what? And to differentiate it up, let me put in some numbers around so that we know what's happening. Okay, so yes, the first 2 get deleted, so it became 3, 4, 2, 5, 2, 6, 2, 7. The first 2 get deleted. Are there more answers possible? Oh my god, yes, there are more answers possible. The second 2 also got deleted. Backtracking. So answer was possible by deleting the first 2. Answer was also possible by deleting the second 2. It turns out answer was also possible by deleting another 2. And these are all the 2s that you could delete. So backtracking is giving you all the answers possible in the way it has been programmed.